Hi Travis. Hi Wayne. This is the second video lecture for the probability graduate level class. And what we want to do is we want to start today by looking at some, if you will, probabilistic facts. So based on the definition. And then we're going to prove those facts along with examples. And then we're going to learn about conditional probability and look at an example or two of that and ways of looking at conditional probability as well. Okay, so let's go ahead and get started. So you'll remember from the last video lecture, our first one, that we had the definition of probability, which really had three characteristics. One was that the probability of an event was between, it was a number, it was between 0 and 1 inclusively. It could be 0, it could be 1. The probability of the sample space was 1. And if you took the probability of a union of mutually exclusive events, that was equal to the sum of the probability of each event involved. Well, based on that, here's a fact. So, some facts about probabilities. The first one is given an event A and its complement A prime is the complement, then the probability of A is equal to 1 minus the probability of A complement. Now, A complement is everything in the sample space that is not in A. It's the set of everything in the sample space that isn't in A. Okay, so it's the opposite, if you will, of that. We're going to do a proof of this, but a Venn diagram is a pictorial representation, we saw this last time, of set theory and involving set theory facts. And here we can use this in the probability setting for a Venn diagram. Use a Venn diagram in this setting. And so here I think of this box as being the sample space. And what we're trying to figure out here, or trying to show, that the probability, if you will, the worth of this set A really is equal to 1 minus the probability, or the worth, of the complement of A, which is what's outside of A. And if you remember the sample space, its worth or its probability is 1. So we think of this square, if you will, being worth 1, like a piece of land worth $1. And what we're saying is the probability of this part of the land is the same thing as 1 minus the worth of this part of the land, what's outside of that. So that makes sense. But let's do a proof here. So, first of all, note that 1 is equal to the probability of the sample space. That was a fact from the definition of a probability. And now we're going to rewrite the probability of the sample space as the probability of A union A complement. So the sample space is the same thing as A union A complement. So if you take A plus everything outside of A, you get S. Now what there is to notice here is that A and A complement are mutually exclusive events. And so we had that definitional fact about probability said if you union up mutually exclusive events and take their probability, that's the same thing as the sum of each event, each mutually exclusive event. And so here, if I solve for the probability of A, I just subtract probability of A complement. So we have the probability of A is equal to 1 minus the probability of A complement. And that proves the facts. I put a little box there to indicate the end of the proof. That's what we have. I'd like to do an example where that's involved. An example I'm going to do has to do with tossing a coin twice. Okay? I'm sorry, rolling a dice twice. So a die is rolled twice. And so the problem that we want to know, or problem is we're going to let A be equal to at least one even number is obtained. So that's an event. And what we want to do is we want to find the probability of that. I'm going to do this in two ways. But for both ways, I want to go back to thinking of this random experiment of rolling a dice twice and thinking, well, there's a sample space associated to it. The sample space associated, I'm going to write it out, it's going to take me a few minutes, will consist of the outcomes for two dice rolls. Well, you could get 1, 1. You could get 1, 2. You could get 1, 3. You could get 1, 4. You could get 1, 5. You could get 1, 6. And those are all the outcomes available in this random experiment where the first dice roll is a 1. But then you could have gotten 2, 2, 2, 2, 3, 2, 4, 2, 5, and 2, 6. Could have gotten 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, and 3, 6. Could have gotten 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, and 4, 6. Could have gotten 5, then a 1, 5, 2, a 5, 3, a 5, 4, a 5, 5, and then finally a 5, 6, and then lastly, the first die roll could have been 6. You could have gotten 6, 1, could have gotten 6, 2, could have gotten 6, 3, could have gotten 6, 4, could have gotten 6, 5, and you could have gotten 6, 6. And that's the sample space where, because of experimentation with fair dice, that it's found that each one of these outcomes is equally likely to occur. Okay, so what we want to know is what's the probability of at least one even number occurring. So this is my first way. The probability of at least A, which is the probability of at least one even number. Okay, and so what I'm going to say is that's equal to the number of ways of getting at least one even number over the number in the sample space. And this is true because of our sample space consisting of equally likely outcomes to occur. And so here I'm going to go back and look at my sample space and take notice of how many of the outcomes have at least one even number. Well, there's 1, 2, there's 3 in this row. In this row, well, there's a 2 in each one of them, so there's 6. So I've got 9 total. There's 10, 11, 12, okay? And then here's 18 of them, because there's 6 more. And then there's 19, 20, 21, and then 6 more makes 27, I think. So there are 27. 36 in the sample space. And so that's my first way of doing the problem. The second way, involving the formula, is that we say the probability of A is really equal to 1 minus the probability of A complement, opposite of A, that's equal to 1 minus the probability that the opposite of at least one die roll is even, is that no die roll is even. No die roll is even. And so that is equal to 1 minus the probability both die rolls are odd. So that's the number of ways both are odd over the number in the sample space. And here, this calculation is a little bit easier just to count because there's fewer outcomes where both of them being odd. But let's look. So 1, 2, 3, none in here. 4, 5, 6, none in here. 7, 8, 9, none in the last round. So my answer here, if I go back, is 9, or I'm sorry, I made a mistake here. It's 1 minus this. So my answer is 1 minus 9 out of 36. And of course, let me write that real low here. That's 27 out of 36, which is the same answer we got in the first way of doing it. So this second way can be considered a little easier because the number that we have to count is smaller than what we had to count in the first way. But you get the same number. All right, well, let's look at a second property of probability, second fact. Fact is that the probability of A union B, two events, we're not saying they're mutually exclusive, is equal to the probability of A plus the probability of B minus the probability of A intersect B. Well, again, I'm going to turn to a Venn diagram to help understand this. So here's my sample space. Here's the event A, here's the event possibly B. Say they're not mutually exclusive, whether they are or not, it doesn't matter. But that's kind of a generic two-step Venn diagram. Now, again, we're going to think of this as like the probability of the word, where the probability of the box, the sample space, is $1. 1. And then we're looking at the probability of A union B. The union, A union B, is this region plus this region. So it's this region right here. We said, what's the worth of that? Well, the answer ought to be, it should be the worth of just A plus the worth of B, but we've counted this region twice. Okay? Once more count A, once more count B. So we need to take away one time. That region is the intersection between A and B, so we need to take away its worth, which is the probability of A intersect B once. So that's why it's true, but let's give a proof more with a little bit more details. Maybe not with all details, but a little bit more details where set theory is involved here, but I'm going to skip some of the set theory details. Well, the first thing I want us to notice is the following. The probability of A can be thought of as the probability of this set. It's A minus A intersect B. That set union A intersect B. Okay. So A minus A intersect B is everything in A that's not in the intersection. So we're looking at this part. Everything in A that isn't in the intersection between A and B. So that is this part of that. then union A intersect B. That's this part of that. So that's all of that. It's this and this. Well, that has broken A into the union of two mutually exclusive events. And so that's equal to, by the definition of probability, is the probability of A minus A intersect B plus the probability of A intersect B. So that's what I can write down for the probability of A. It's equal to this addition. Well, we can do the same thing for the probability of B. So similarly, the probability of B, without writing, skipping one step, I should say, that's equal to the probability of B minus A intersect B plus the probability of A intersect B. So if we add the probability of A and probability of B together, well, that's equal to the probability of A minus A intersect B plus the probability of A intersect B plus, I'll write down this line, the probability of B minus the quantity A intersect B plus the probability of A intersect B. Before I go on, let us look at these first three probabilities with this Venn diagram. The set A minus A intersect B is this part of that. A intersect B is this part of A. So we've got this region plus this region's work, and then finally this part, the probability of B minus A intersect B. The B minus A intersect B is this part of B. So we've got this part, and this part. And if you look at them individually, you see that they're mutually exclusive. And we're adding them. So using in the definition, one of the properties in the definition of probability, kind of the reverse order of it, if we have the sum of mutually exclusive, the sum of probabilities of mutually exclusive events, we can write that down as the probability of their unions. And that's what I'll do. Unclear. Let's see if it's clear. I think it's clear. There. So this is equal to the probability of A minus A intersect B union A intersect B union B minus A intersect B. And then plus the probability of A intersect B. That's what this equals. And let me write what it was. Let me write this above. So the probability of A plus the probability of B, that's where we work, is equal to this. Now look, let me draw the Venn diagram over here very quickly. Here's A, this is our sample space, is the box, here's B. Look, A minus A intersect B is this part. Union A intersect B, that's this part. Union B minus A intersect B is this part. If you union all those up together, you get this plus this plus this. That's nothing more than the probability. So this set in this squared bracket is A union B plus the probability of A intersect B. All right. So if we look here, we have the probability of A plus probability of B is equal to this. So solving for the probability of A, union B, we get that that's equal to the probability of A plus the probability of B minus the probability of A intersect B. So that ends that proof. What I want to do next is an example where we might use this. And we'll do this example in two ways. Here's my quick example. Let's say a die is rolled twice. Let's let A, so this is an event, be the event that at least one roll is a 2. 2 is involved in the outcome. And let B be equal to both rolls are even. Okay, and the question is to find the probability of A and B. These are not mutually exclusive events, for if you intersect A and B, there are going to be things in common. So we don't know what the probability of A and B is. So here's my first thing I'm going to do is I'm going to repeat what the sample space is, but I'm going to do it kind of quickly here. So we have 1, 1, 1, 2, and it goes all the way up to 1, 6. And then we have 2, 1, and it would go all the way up to 2, 6. We have 3, 1, and it goes all the way up to 3, 6. We have 4, 1, and it goes all the way up to 4, 6. We have 5, 1, and it would go all the way up to 5, 6. And finally, the last row will consist of outcomes that start with 6, 1, and go all the way up to 6, 6. So I'm not listing all of them, just listing a few of them. So if I say the probability, so here's my first row. The probability of A union B is equal to, it's the probability that at least one die is a 2, or, that's what union means, both rolls are even. And since I'm looking at a sample space that consists of equally likely outcomes, what I can say is that this is probability is equal to the number of ways of at least 1, 2, or both rolls even over the number in the sample space. Okay, so I don't have very much room here. I'm going to write the answer over there, I guess. Maybe I'll write right here. But let's count all the outcomes that fit at least one of these criteria. At least 1, 2, or both are even. In this first row, there's only one outcome which that fits one of those categories, at least one of those categories. There's a 2 here. Okay, so there's 1. In here, all of it fits, so there's 6. In here, there's only 1. The one that's 3, 2. In here, remember one of the categories, you either have a 2 or both of them are even. Here, both of them are even. 4, 2, 4, 4, and 4, 6. So there are 3 that fit this category. There's 5, 2. That's the only outcome in the 5th row that fits the category. And here there are 3 of them that fit this category, fit the category of both of them being even. There are none in the 6th row where, well, I'm sorry, there's 1 where there's a 2, but it also is included in the both of them being even. Okay? So here I have 7, 8, okay? I think I have 15. So it's 15 out of 36. That's the answer I get. You can, of course, reduce that. That's what I'm including. And that's my first way of doing the problem. Okay, the second way of doing the problem is using our fact. So the probability of at least 1, 2, or both rows even, by our fact is equal to the probability of at least 1, 2, plus the probability of both rows even, minus, let me write down here, minus the probability of at least 1, 2, and, that's what intersection means, both rows even. Let me swing the camera back and let's look back at our sample space. Okay, so the first category I'm looking at is at least 1, 2. So at least 1, 2, I'm going to erase these. With at least 1, 2, there is 1 here. There is 6 here. There is 1 here. At least 1, 2. There is 1 here. There's 1 here, and there's 1 here. That's a total of 11. Okay. So I'm going to come back. I'm sorry it takes so long. I'm going to come back over here. And so my answer for this one, at least, there are 11 out of 36. The number of ways this can happen out of the number of samples. Plus, probability both are even. Let's go back and count that. Both are even. Well, none happen here. 3 happen here. Both are even. None. Here there are 3. None, because the first one is 5. And here there are 3. So there's a total of 9. So that's 9 out of 36. But some of the things that we counted are in both. And so we need to take those away. So the ones that have a 2 and both are even, count those. Well, there's 3 here. They're both are even. There is 1 here that has a 2 and both are even, and 1 here, so I need to take away 5 out of 36. I'll write that down. Well, that's 20 minus 5 out of 36, and of course that's 15 out of 36, which is what we obtained when we did it the first time. Okay, so that's good. We got the same answer both times. That's good. All right, another fact that I want to prove about probability. So it's a property of probability. It's a very short fact. Is that one of the events from my sample space is the empty set. So it's a subset of the sample space. And the probability of that is equal to 0. So here's my proof. I have room right here. Note 1 is equal to the probability of the sample space. But the sample space is enough more than the sample space plus no, which is the empty set. These are mutually exclusive events. So this is the probability of the sample space plus the probability of the empty set. Well, I didn't have as much room as I thought. Let me characterize that a little bit. So, what that says is that 1 is equal to the probability of S plus the probability of the empty set. Well, so 1 minus the probability of the sample space equals to the probability of the empty set. But the probability of the sample space, by definition, is 1. So 0, which equals 1 minus 1, is equal to the probability of the empty set. So we have the probability of the empty set is equal to 0. And we'll use that a little later on in this lecture. But I'm not going to do an example of that. Okay, the next thing that I want to talk about is something called conditional probability. So I have room to write its definition here, and I'll do it. We're going to let A and B be two events with the probability of B being different than 0. Then the conditional probability of A given B is denoted by probability of A with a slash B, and defined by probability of A given B, this conditional probability of A given that B happens, is equal to the probability of A intersect B over, so it's divided by the probability of B. So that's why we had to have the probability of B is different than 0, because we're divided by it. We should look at an example. Okay, we're going to look at a very simple example first. So the setting of this example is a deck of cards, standard deck of cards. So suppose a card is randomly selected. That means everything's equally likely, almost. Randomly selected from a well-shuffled, now everything's equally likely. Standard deck of cards. Standard deck, there are 52 cards, there are 4 suits, there are diamonds and hearts and clubs and spades, clubs and spades being black, diamonds and hearts being red, and in each suit there are cards ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king. Find the following. A is the probability heart was selected. Part B, the probability that a heart was selected. The heart was on one card being drawn, given, okay, a red card was selected. And part C is the probability of a heart given black card was selected. So that's my question. Let's do it here. The first problem, part of this problem, is not a conditional probability. It's not a given. Okay? There's no given involved. So for part A, we just want to know part A, the probability of a heart. Well, that's equal to the number of ways a heart can happen. Heart can be selected over the number in the sample space. If everything's equally likely and in picking a card, it is from a standard deck that's well shuffled. And so the number of hearts there were 13 of them, ace through king. And the number in the sample space, well, in the deck, there's 52 cards. So the answer is 13 out of 52, or 1/4. Okay. Part B is a conditional probability problem. It's the probability of a heart given red card. Okay. I'm just going to mention it right now, but we're given more information than just than no information. Someone is telling you that a red card was selected. So a card was selected, it was red. Now what's the chance it was a heart? Okay, so here, the way we would do this is the probability of heart and red, by definition, over the probability of a red card. That's equal to, well, is the number of ways of getting a heart and red over the number in the sample space. That's the top probability. All divided by the number of ways of getting a red card over the number in the sample space. So probability of heart and red is this fraction. Probability of red card is this bottom fraction, so I got a complex fraction. The top of the first fraction, heart and red, if you got a heart and a red card, there's only 13 ways to do that. You really got a heart, that's what happened. And that's out of 52. Divided by number of red cards, there are 26. There are 13 hearts and 13 diamonds out of 52. So that ends up being 13 out of 26, which is 1/2. So the probability change of getting heart, if you knew this other information. Let's look at the last part. Last question of this part, part C, the probability of heart given black card. Well, by definition, this is equal to the probability of the heart and black card over the probability of the black card. Each one of these is a fraction, when our sample space being equally likely events where the sample space is each card in the deck. This is the number of ways of getting a heart and black card. Over the number in the sample space. Over the probability of the number, I should say, of getting a black card. Over the number in the sample space. And what that's equal to, well, there are no hearts that are black. They're all red. So this is 0 out of 52 over, this is 26 over 52. So we end up getting 0 out of 26, which is 0. So the chance of getting a heart, given that what was selected was a black heart, is 0. And that really involves, in this first probability computation that I did, that the intersection between these two events is the empty set. And the probability of the empty set is 0. That's what we see right now. If that comes into play. Okay. Let's look at another example in a second. But first, yeah, let's do one more example. So another example, kind of a common setting where we do some basic probability, has to do with taking a card, flipping a coin, rolling a die, some combinations of those. And also lots of times we're choosing things out of a container, balls out of a container, colored balls out of a container. And so here is one of those last type of examples. So an urn contains 8 white balls and 3 red balls. Okay. 2 balls are selected, one after another, without replacement. So you're not replacing the first ball that you selected. And they're done at random. So here's the question. Find the probability that the second ball is white given the first ball is red. Okay, that's our problem. So here's what I would do. I would use the definition of conditional probability. So this is the probability that the first is red and, that's what intersection means, the second ball is white over the probability the first ball is red. Okay, the probability the first is red and the second is white. Let's think about this. How many ways can that be done? We're thinking that the sample space, outcomes that are possible, are equally likely to occur. So let's see. So for the first probability is first is red and the second is white. The first thing I got to do is get a red ball. What's in the urn? There's 8 white and 3 red. So it means there's 3 ways that I could have picked a red ball to start. And then how many ways for each one of those 3 red balls is that the second ball could be what? Well, there's 8. Now, how many ways are there to pick 2 balls without replacement? Well, there's 11 balls to start off with, 8 and 3. And then once for each one of those balls that could be chosen, there are 10 remaining. So that's the probability first is red, second is white. All over the probability that the first is red. Well, the probability that the first is red is, how many ways can you pick a red ball in the first one? 3. And then you've satisfied the requirement that the first is red. So it doesn't matter what you pick on the next ball. How many ways are there to pick another ball? There's 10. And this would be over 11 ways to pick the first ball, and then 10 following that. And so what we end up getting here is 3 times 8 over, I think, 3 times 10. So we end up getting 1/4. So there's 1/4 chance that the second ball is white given the first ball is red in this setting. So we're just following the definition of conditional probability. Okay, here's a fact that I want to tell you involving conditional probability. It says, if the sample space consists of equally likely equal events, and that's all we look at in our examples for conditional probability. Okay. Then, the probability of A given B is conditional probability can be computed by reducing the sample space to only events where B occurred. Only the outcomes. B occurred. And then computing the probability of A from this reduced sample. Okay? So that's how you get the probability of A given B. Okay? So you reduce this, if you can, if everything is equally likely in terms of the outcomes, reduce the sample space, okay? And then just compute the probability of A, and that will give you the probability of A given B. It's equal to the probability of A in the reduced sample space, where that's the number of ways A could happen from the reduced sample space over the number in the reduced sample space. So let's think back here. Let me write something first. So, in other words, in other words, when all outcomes are equally likely, we can put ourselves in the given situation and find the probability that A given B has occurred. Okay. By just finding the probability that A has occurred. Let me give you just some verbal examples, not writing them down. That's the example we looked at before with the cards. So you remember we were talking about a heart being chosen. Part B of that example, a heart being chosen given that a red card was chosen. Well, there were 52 cards in the deck, 26 of them were red. Out of those 26 red cards that you know one of them was chosen, there are 13 of them that are hearts. So there's 13 out of 26. That's 1/2. That's what the answer was. Is that okay with everybody? And the other part was that a problem was that we had the probability of heart given a black card. Well, when you say you chose a black card, that meant that you got a spade or a club. So there's no way that you got a heart. None of the outcomes when you get a black card are heart. So it's 0. Put yourself in that reduced sample space of only having clubs or spades. There are 0 hearts in there out of 26. 0 out of 26. You saw that in our calculation. If we revisit the earn problem that we just did just a minute ago, so this one I'll write down. Okay, remember what the earn problem had? It had 8 white, 3 red. Okay. And what it said was we were trying to find the probability second is, I think, is white, given first is red. And we got an answer. We did the problem. It was 4 out of 5, I think. 8 out of 10. And so here's what I'm going to tell you. You put yourself in this position of that the first ball was red. So if the first ball you selected was red, what's left in the urn? Well, what becomes in the urn is 8 white and 2 red. So now, that's the situation you're in, and you're choosing a ball at random, 8 whites, 2 reds. And so there are 10 balls, and out of those 10, how many are white? That's what we'll know, is that's white. So there's 8 out of 10, which is 1, 4. That's how. Well, let me do one more thing, and then we'll end this lecture based on this last thing. But as I race the board, let me say, often computing conditional probabilities, especially when you're being asked what happens next, given what happens previously, are not so hard to calculate because you put yourself into the what happened previously case. You reduce the sample space when all things are equally likely. Computing a conditional probability when the opposite is occurring, when they tell you to find out what previously happened given what happens in the future, that's a little bit more difficult, but we have a formula that helps for that, and we'll get to a little later on. Not during this lecture, but the next one. Well, we'll conclude here with the fact. If somebody says, what's the probability of A intersect B? Well, if the probability of B is not 0, that's the same thing as the probability of A given B times the probability of B. Truthfully, and in this case, they are the same with the probability of B's, 0 or not. But it really stems from the conditional probability case. And we need for this to be defined, the probability of B to be different from 0. So, okay. Probability of B is different. That's what we have. All right, let's look at an example and prove that. So let's look back at the urn problem. We got 3 white, 3 red, 8 white. 2 balls are chosen without replacement. Somebody says, find the following probability. The probability that the first is red, first ball chosen is red, and second ball chosen is white. Well, we could do this by counting all the ways that this can happen, but as I said earlier, if we use this formula, the conditional probability sometimes is easy to calculate, but what I can say is this is the same thing as probability the second is white, given the first is red, times the probability that the first is red. So this conditional probability we can calculate by putting ourselves in this position. Okay, we've chosen a red. What's the chance now the second ball is white? Well, that's 8 out of 10. Times, what's the probability that the first is red? The probability that the first is red, so in this situation, is going to be 3 out of 11. Okay? And then that's what we have. Okay? So that's the answer to our problem. It's not so hard to calculate. All right. Well, thank you very much for your time and patience, and that will conclude this lecture.